Welcome to qnawire.
Hi, so for this question, the first thing that we need to remember is the relationship in between delta G and the value for delta G naught and equilibrium constant or the equation product that we have. In this case, we're dealing with gas products, so we're going to use QP because this is the equation for the gases that we have in our solution. So the chemical reaction that we are dealing with is the following. We're going to be producing a solid that does not enter into our equilibrium equation because that is a pure substance. So if we work out the value for Qp for this reaction, we're going to have the pressure of water squared, because the coefficient over here is 2, divided by the pressure of H2S squared as well, times the pressure of SO2. So, so if we substitute the values, we are going to get the pressure of water. In this case, it is going to be 2.5 atmospheres. I'm going to omit the units just for sake of clarity. For the pressure of H2S, the value turns out to be 0.01. This is going to be squared. And the value for SO2, it is going to be 0.025 atmospheres. With this, the value for Q that we're going to get is 2.5 times 10 to the 6. So now the only thing that we need to do is employ this value for Qp in our original equation. We're given the value for delta G naught, which is minus 90.88 kilojoules. And finally, we need to take the values for RT and the logarithm of 2.5 times 10 to the 6. So now the only thing that we need to do is substitute the values. The value for the temperature, it is 175 degrees Celsius. So we need to convert that into Kelvin. So degrees Celsius, which turns out to be in Kelvin, we simply need to add 273.15 to that value. So in Kelvin, the temperature is going to be 448.15 Kelvin. Okay. Now, here a little comment. Probably there is a typo in the problem because this value is normally and should be in kilojoules per mole, since it's a delta G naught for the whole reaction. So, also, otherwise, that value for delta G does not make sense because if you check up the units for the R constant, you're going to realize that things are not going to match up properly. So in this case, the value for R is 8.314 joules per mole Kelvin. This means that at the end we need to transform these kilojoules into joules, but we're going to do it after we do some basic operations. The temperature, we need to use the temperature in Kelvin. And the logarithm of 2.5 times 10 to the 6, which is 14.7318. So after doing the operations, we end up with here Kelvin and Kelvin cancel out. This value does not have units because it's just the logarithm. So this is minus 90.88 kilojoules per mole plus 54,889.5 joules per mole. Here we can convert either of the units directly, but since the answer is asked in kilojoules, the result would be minus 90.88 plus 54. Let's round it up for this to make more sense in the units that we have initially. 54.89 kilojoules per mole. What I did from here to here is simply dividing this quantity by 1000 in order to get it into kilojoules. So with this, the final result is minus 35.99 kilojoules per mole of reaction. And that would be the final answer. Now, if you want to check up if this result actually makes sense, we know that the reaction is going to be spontaneous, and we are given that the value for Q, it is going to be way a super large value. That means that we have a lot of the products. So if we have more of the products, the value for delta G should be lower than the value for delta G naught, which is true in this case. So the reaction becomes, in a certain way, less spontaneous. And that would be your final answer. Thanks.